Before we get into problem set number 4, question number 7, I thought it might be useful to revisit the theory of hypothesis tests. And before we do that, it's worthwhile reminding ourselves on what the difference between standard deviations and what standard errors are. So in question number 5 and number 6, we had a curve kind of like this. And the curve represented the distribution of observations. And the line down the middle was the sample mean. So we're comparing a fixed value, the sample mean, and the observations around the mean. And the distance from the mean was measured in standard deviation units. So we had a sample mean, standard deviation, and observations. I guess the kind of key way to remember that would be observation deviation. In question number 7, we changed some things up. We still have a distribution kind of like this. In our case, it's a t-distribution. But the line down the middle is not the sample mean anymore. It is now the population mean for a fixed value. And the distribution is not observations. The distribution is now sample means. So we only have one sample mean, but the underlying distribution would be more sample means. And our distances are not standard deviations anymore. Our distances are now measured in standard error units. So observations, deviations, and sample means, the distribution of sample means correlate, or we would use standard errors for. So hopefully that clarifies at least a couple things there, rather important concept. Moving on to hypothesis tests. So for the moment and for this particular example, I'm really just going to focus on two-tailed tests. So we're talking about a hypothesis where something is or a test on whether or not something is or is not equal to whatever. So in our case, in question number 7, we're asking whether or not the long-term historical mean is equal to 211. So the opposite of equal, so the null hypothesis is whether or not it's equal. The opposite of that would be not equal, which means it could be less than or it could be greater than. The fact that there are two options as our alternative to the null hypothesis, those two options mean we're talking about a two-tailed test. So our null hypothesis is that the long-term mean is equal to 211. How are we going to reject the null hypothesis or fail to reject the null hypothesis? So we have our sample mean of 167. What are we going to do with that? And ultimately, we're going to evaluate our null hypothesis by saying, well, if our sample is close to our population mean, then we're going to say it's okay. And we will fail to reject the null hypothesis. So we'll go with, yeah, it equals 211. If our sample mean is not close to our population mean, then we will reject the null hypothesis. Well, that sounds all well and good, but terms like close and not close are rather vague, so we need to put actual numbers to those. So where did those numbers come from? Really, that's the basis of a hypothesis test. So we have our test, we have our null hypothesis that it is the long-term mean is equal to 211. We will also, as step number 2, have to assign a confidence level. So how certain do we want to be in our answer? And confidence levels are expressed in terms of percentages, and those percentages really relate to the area under the curve. So we're going to say that our sample, or we will call our sample close to 211, if there is for instance, a 90% chance of having observed our sample, given that the actual long-term mean was 211. So under the null hypothesis, the long-term mean is 211, and we will fail to reject, we'll kind of accept that idea as long as there was a 90% chance of observing what we actually saw. And I keep using 90%. Often we use 95. In question number 7, we happen to be using 90. So that confidence level, that 90%, defines how close our observation needs to be to our hypothesized value. And if it is in that range, then okay, we will fail to reject. We'll kind of accept it. And conversely, if there is a 5% chance, or I guess not a 95% chance, of observing our sample mean under the null hypothesis, then we will reject it. We'll say it is too unlikely to have observed this value under the assumption that this is true, so this assumption must be wrong. Well, I shouldn't say must be wrong, but it is unlikely to be correct. So that step number 2, that assigning of the critical value, is a very critical step, because that is what everything else is based on. So in question number 7, we assign a critical value of 90%. So as long as there's a 90% chance of observing what we saw under the null hypothesis, then we'll say it's close enough. So that means there's a 10% chance that this value is actually true, but we're going to reject it anyway. So here is our rejection region. That is, there's one over there, and there's one over there. So if all of this is 90%, then this plus this has to be 10%. And since it's a two-tailed test, because all we're interested in is not being 211, it could be less than or greater than, we will take that leftover 10% and we will assign 5% over there, and we will assign 5% over there. So if our observation, if our observed sample mean falls in this region or in this region, then we will say it is too far away, it is too unlikely to have observed this under the null hypothesis. So our null hypothesis is probably incorrect. That sets us up for the 3 different methods that we can use to do the formal hypothesis test. The first method is the critical value, and the critical value gets compared to the t-score. So let's just start with the critical value. What is that? Well, I've already said that we have this kind of cutoff here where we will reject the null hypothesis if our sample falls in this rejection region. So that kind of implies that we need a different color. That implies that we need to define some sort of threshold, some sort of line here that differentiates where we'll accept a result and where we will reject a result. This line, this threshold, is the critical value. So it differentiates, or I guess we could say it identifies where our rejection region is going to be. And so there's also one over here because we have a two-tailed test. The t distribution, the normal distribution, is symmetrical. So the distance from here to the critical value is the same as the distance from the mean to the critical value over here. I will also mention that the critical value is a measurement relative to the mean. So it is a distance of sorts from the mean to the beginning of the rejection region, and from the mean to the beginning of that rejection region for a two-tailed test. So the critical value, again, it's our threshold. Here's the Excel function for it. So in question 7, we're talking about a t distribution. So we have the t version of this. We need to give Excel a probability so it can tell us a distance. And that is what the .inv version of the test does. And since it's a two-tailed test, we use the .2t function to give that. Excel, in its kind of awkwardness, for the 2t or dot 2t function, we give it an alpha, so the small number, 0.1 in this case, and a degrees of freedom. And if you remember, degrees of freedom is the number of data points minus 1. So this will give us a critical value such as 2.3. 2.3. We'll just draw that in there. I just kind of made that number up. So this says that the rejection region starts at 2.3 standard errors away from the mean. Remember, we're using standard errors because in this particular problem, our distribution is based on sample means. We would still get a critical value if this was a distribution of observations, but then this would be 2.3 standard deviations away. So in our question, it's again the distribution of means, so this is 2.3 standard errors away, and that is our threshold. So if our sample mean is more than 2.3 standard errors away from our population mean, meaning our sample mean is in here somewhere, then our sample mean falls in the rejection region, and we will reject the null hypothesis. Similarly, if our sample mean falls in here, if it is more extreme, in this case on the negative side, than our critical value, then it falls in the rejection region, and we will reject the null hypothesis. So we can use this equation, which again uses just the probability and degrees of freedom to identify how far away in standard error units our threshold is. Now that by itself is insufficient. It's our cutoff, but we still have to compare that cutoff to our data. And our data needs to be transformed into the same kind of units as the rest of this curve is. So if our critical value was 2.3 standard errors away, then we need to convert our data, our observed sample mean, into standard error units, a number of standard errors. That conversion is done using the t-score, or the z-score if this is based on a normal distribution. So the t-score is the number of standard errors that our sample mean is. And it also has an equation here. We take our sample mean and we subtract it from the population mean. We divide that by the standard error. So the sample mean comes out of the data, mu comes out of the question, that is our long-term mean or the fixed value, and the standard error also comes out of the data. So we calculate that, and that again kind of converts our sample mean into standard error units, a distance from the mean. In question number 7, we'll see this earlier, we see that a sample mean of 167 is actually way over here at minus 5 point something. We'll just say it's minus 5.5. So this is minus 5.5 standard errors away from the mean. That's where our sample mean is. So way over here. So our first way of deciding whether or not we should reject our null hypothesis is comparing our sample mean via our t-score to our critical value. So the critical value is the threshold. If our sample is more extreme than the threshold, then it is unlikely to follow or to originate from this long-term mean, and we will reject the null hypothesis. Well, our critical value was 2.3 over here, which means this is negative 2.3. So if that's our cutoff, we're at minus 5. So we're definitely more extreme than our critical value. We are in the rejection region, and so we will, in fact, reject the null hypothesis. So that's the first method. Given that it's a 14.5-minute video, I'm actually just going to stop it here, and then we'll revisit the same thing using the p-value approach.